Now that we have covered the main body of content, work content, for week number 4, which is the different additive manufacturing or 3D printing technologies, let's look at a couple of real-world examples, a few videos of how these technologies actually produce the parts that we discussed, and sort of draw back on the information that we already covered, just to put 2 and 2 together and get a better understanding of how these technologies work. So if we start off with SLS and SLM, so Selective Laser Melting, Selective Laser Sintering, if you remember, this was the technology that used a laser to melt metal powder that kept being fed onto the workspace. So let's see what that actually looks like over here. This example, we can see that we have a bed of metal powder, and these sparks that are flying is actually the laser that's melting that layer of powder into the shape. And you can start to see the shape forming over here, right? In one of the layers. So this is maybe layer 1 or layer 2 or layer 3, not quite sure, but it's one of the layers of the model. So the laser finishes melting this layer, and then what should happen is a little roller, as you can see it's coming back and forth right now, is depositing another or the next layer of powder on top. So you can see the previous cross-sectional area or layer that was just printed has now disappeared under that new additional layer of metal powder. And then the same process where the laser melts the next layer, so on and so forth. It gets repeated until the 3D printer itself goes through all of the layers of the model and finishes printing each one. And after it does that, the model can be removed from the workspace, right? And the additional powder from the workspace hasn't been used can be reused and recycled, fed back into the loop, right? So if we go on to the next video, this one over here, this one sort of shows the schematic that we also saw during the lesson with the main workspace over here, the laser, the roller, and the feed powder beds to the left and the right, and the pistons moving the build platforms up and down. So you can see initially the main workspace platform moves down one layer, and the right feed powder bed platform moves up, and this roller is now going to move across and deposit this feed powder material onto the workspace for the first layer of the 3D printing process to commence, right? So as you can see, one layer's worth of material has been moved or deposited from the material bank onto the workspace, and now the laser is melting the cross-sectional area of the first layer. Right? Once it does that, the second powder bed sort of moves up to continue feeding it. This is a dual powder bed supply style system. You can also have one powder bed style, but then the roller has to go and do a back and forth motion for each, layer deposition. Whereas in this dual powder bed feed method, it only needs to move across once per layer, right? So it deposits the second layer onto the workspace. Then the laser melts the second layer on top of the first, and so on and so forth until all the layers have been completed of the model. And as you can see, the pistons move up and down, moving the build platform and the feed platforms up and down respectively. And at the end, right? Once the model is complete, you will have to remove your model from this block of the workspace, right? Which includes the model and the additional powder material around it. Now, if you remember some of the advantages that we discussed of SLS and SLM are that you can use metal. So this could potentially be metal powder that is being melted. It could be aluminum powder. It could be stainless steel powder. It could be even maybe if you wanted copper powder or any other kind of metal that can be melted using a laser. I believe there could also be, some plastic, thermoplastic powders available over there, but the main use of these machines, because they're so expensive, they're used mainly with metal because most of the other 3D printing technologies, as we've discussed, they cannot process metal. So it'd be a bit of a waste to use such machinery to produce parts from thermoplastic, considering the other much cheaper alternatives that can do that. Now, considering that the workspace or the part is encapsulated or contained within this block of metal powder, you can see that each layer is supported by the powder underneath within the workspace. So another advantage that we discussed is using selective laser sintering or selective laser melting is you would not need support structures to support your model. However, you do need to take account that obviously when melting this, if you create an enclosed surface such as a sphere, that sphere would be filled with this metal powder. So you have to take that into consideration when you design your parts. You'll need to have a hole to be able to remove the internal volume of unmelted powder. Yeah, unless you actually want to keep that inside the model. But in most situations, most applications, you do not want to have that internal powder inside your model. So obviously we're discussing both selective laser sintering and selective laser melting in this one example, because even though the technologies, or there's two technologies, the main difference between them is how, let's say, how much percentage of it you melt. So pretty much selective laser sintering, actually uses sintering, a sintering process rather than a melting process. So sintering is partially melted material, so it's not fully or completely melted. To completely melt it, as in selective laser melting, you need to shine the laser on the cross-sectional area for either much longer or to increase the power of the laser itself to be able to completely melt the powder in the cross section. Right? And as you may infer or as you may assume, right, metal powder or metal itself, it requires a lot of energy to be able to melt. So if you have a laser beam, it can only contain so much energy to be able to melt it. So to have such a powerful laser to completely melt the metal powder is expensive, and it will use a lot of electricity or power to actually, provide sufficient energy to melt the powder fully. So, in some applications, it's faster. Yeah, it uses less electricity, so cheaper from running costs to use selective laser sintering. So in this case, as we have discussed, selective laser sintering is more used for prototyping processes. Selective laser melting is used more for end parts. Yeah, so parts that you want to put into direct application, right? So not just as a prototype part, a part that you want to test to see if it fits, and then later on you create a finished part. Using the selective laser melting process, you would directly create the finished part. So that's the main differences, but technology or process-wise, they follow the same steps or the same operation. All right, let's have a look at another one where you can actually see a bit better the equipment and the components. So you can see the laser over here. There's a cooling fan attached to the laser to cool it down, because considering the amount of power output this laser has, it can easily overheat. You need a thermal sump over there to sort of direct all of the heat produced, in the component by the laser, because not all of the heat is directed down onto the build platform or workspace. Some of the heat is retained within the laser module itself. So, similar analogy as in a computer, right? You have a motherboard, you have RAM, you have the graphics card, and the motherboard or the CPU itself and the graphics card, they have a thermal sump, which is a little metal plate with a heat sink on top, which sort of directs and dissipates the generated heat from these components being used. So it's a similar concept to this, and you have a fan on top to sort of have a constant airflow across this heat sink to sort of cool down the laser, so the laser doesn't get damaged and it can keep working, and it improves the longevity of the laser. Okay, so you can see what's happening right now is a layer of metal powder has been melted. You can see the cross section, they've created a little square on there. And now what's going to happen is, you can see it's sort of moved down. It's changed color because of the motion of the build platform. It moved down. Yeah, it's moving down. And now what's happening is the roller underneath is depositing a new layer of powder. So you can see the cross-sectional area that's been melted over here. It sort of disappeared because there's a new layer of powder on top. So once that powder layer deposition is done, the laser can continue on to the next layer. As you may have seen in this model, yeah, as opposed to the previous one, this had a dual feedback, so the roller only had to go across the workspace once. In this example, I believe it only has one material feedback. So the roller had to go across once and come back, return to its home position. And as you can see, that took a larger or a longer amount of time to prepare each layer, right? Whereas in this situation, you would sort of not half the time, but pretty close to that. You'd have at least the material preparation or workspace preparation time for each layer. And obviously, considering most models, there are hundreds, if not thousands, of layers that need to be produced, that time quickly adds up. So, that's why this sort of design with dual feedbacks has been invented. Now, if we can continue watching this video over here. Yeah, the second layer is being manufactured or burnt in. So I just want to mention, as you can see, there's sort of 3 axes of motion over here. So the workspace, yeah, or the build plate moves down. So that's in the vertical axis or the Z axis, right? Here, the laser itself, the laser module, is sort of attached horizontally from left to right, yeah, to a motor which moves it left and right. That's in the horizontal or X axis. And then over here we have another belt tensioning this sort of axis, right? The horizontal sort of arm to which the laser is held, and that moves this whole arm, you know, sort of from the bottom of the screen to the top of the screen. Again, in the horizontal plane, but along the Y axis. So the motor or the laser over here, it has 2 degrees of freedom along the x-axis and along the y-axis, and the third degree of freedom is provided by the build plate in the vertical or z-axis. So in total you have 3 degrees of freedom, and these 3 degrees of freedom are, you know, visible or are present in all of these additive manufacturing technologies, right? If you only had 2 degrees of freedom, that would only allow you to build or to construct geometry in a 2D plane, right? So 2 degrees of freedom, 2D, right? Because you can only do a horizontal sort of a thing, yeah? You can only draw 2 lines pretty much. So if you had 1 degree of freedom, as an example on the x-axis, you can only draw a horizontal line, right? If you have 2 degrees of freedom, so you can move left to right and up and down the screen, right? So in the x-axis and y-axis, you can draw sort of 2 lines that, or, you know, lines in 2 directions sort of a thing, or along 2 directions. And what this would allow you is to create geometry in 2 dimensions, right? So as a sketch or whatnot, general desktop printers, not 3D printers, general inkjet printers, right? They also have sort of, if you ever looked inside of one or you've seen how one works, it also has like a head, yeah, but instead of using a laser, it just shoots ink down at a piece of paper. And this head moves left and right and selectively shoots depending on the words or the image or whatnot, right? So you'd say, but that's 1 degree of freedom, right? So how does it create images or pictures in 2D on a piece of paper? Well, the second degree of freedom is actually provided by the paper actually being fed out of the printer. So pretty much inkjet printers or printers that you might have used in school or at university, they have 2 degrees of freedom of motion. 1 degree of freedom provided by the paper being ejected as it's being printed, and another degree of freedom from the print head or the inkjet nozzle. Right? But in additive manufacturing, because we are not working in a 2-dimensional plane, we are working in 3 dimensions, you need that additional degree of freedom. So we'll see this, and hopefully you'll notice it and perceive it in each of these examples that we see, all of these degrees of freedom. So yeah, you can see it's finished the second layer now. And then it would just continue until all of the layers have been covered, right? So that was selective laser melting and selective laser sintering. Similar technologies, as I said, the only difference was between how fully the material is melted. Sintering, not as much, melting fully, right? So easy way to remember it is with melting, it's fully melted, right? Melting, melted, yeah, similar words. Sintering, because it's a different word, it's similar to melting, but not the same, you know, it's partially, right? So not 100% melted. Let's move on to our next technology. So let's see. So this will be fused deposition modeling. Let's see what example we have over here. So over here, this is more of an industrial. unit for fused deposition models. You can also get desktop examples which are pretty much the size of two regular inkjet printers stacked upon each other. We will see later on they're similar size to stereolithography models. So once we cover that, you'll get a better impression of the size. But this will show you a good example of how it actually works, how it deposits material. So let's continue watching. So as you can see here inside the unit, this is the build plate, and this is the actual part that's being printed. You can see there's sort of two colors. There's one black, which is the actual part, and there's white filament in there as well. I believe the white filament itself, that might be a support structure. So generally, support structures, they can be, either made from the same base material as the part itself, or you can use a secondary material. If your 3D printer is a bit more expensive, a bit more advanced, it can have two nozzles, so you can feed two types of material through it, one for the main model and one material just for the support structures. And the support structure material can be a bit, let's say, weaker, so it's easier to remove in post-processing, or there's some thermoplastic filaments that have an element of water solubility to them, so pretty much they get softer, weaker, they start to dissolve in contact with water. So you can print your support structures from this type of filament, and once your print is done, you can submerge your whole model in a tank of water to sort of dissolve away some of those support structures and get a better finish than by manually or physically removing the parts, using a file, sandpaper, pliers, knives, or whatever. So you can see this is the print head that extrudes the thermoplastic filament through a nozzle that's over here. This tiny little white bit sort of is a bit like a curve, and on the tip, that's the hole of the nozzle. This is where you can see it a bit better. So the tip is over here, and it extrudes the molten filament onto so this is the actual workpiece, right? It's not on the first layer, it's on layer maybe like 70 or 80 or whatnot or something like that, and it's continuing printing. As you can see over here, between the gaps in the model, it does a little jump or a little hop. This is some settings that can be edited, manipulated, or specified in FDM technology. So it's a hop setting, and this has been noticed or has been researched that it sort of helps with avoiding stringing or filament strains going in between the model. It sort of helps with better accuracy and printing quality. So this is sort of the 3D CAD data that's been sliced or it's being prepared to send to the 3D printer itself. So you can see in this industrial unit, it has thermofilament storage area over here underneath. Yeah, so this is where you put your filament, and then it's the machine itself feeds the filament through the machine, going sort of on top and extruding it through the heated end to build on the build plate here on top. And I'm assuming that one of these is the base material for the part, and the second one is a different material for the support structures. So you can see, yes, that's the case. This is for the model itself, and this is for the support structures. right? In this industrial unit, you can also see there's the vacuum and pressure gauge. This is to create a controlled environment inside the 3D printer. Some lower grade 3D printers or fused deposition modeling printers, they might not have an enclosed printing chamber, right? Just to save on costs. Some of the, let's say, wider available models don't have an enclosed chamber, so the ones that hobbyists buy and whatnot. And these ones can be affected by the ambient temperature or room temperature. They can also be affected by the humidity in the air. Let's say if you have one of these 3D printers, not this one in the example, but a different commercially available one that doesn't have an enclosed box, and you put it inside your office or room, and you have a window open and there's a draft of air, that could also affect the quality of the models that it produces. So that's why in more expensive or FDM technologies used for an industrial application, yeah, so used in different companies to create their prototypes, they sort of try to not sterilize but control the workspace and build environment more accurately in terms of humidity, moisture, air temperature, even pressure and whatnot. So it gives you a better idea of some of the elements that can have an effect on your models produced.